Yeah.
pleasure to introduce James Sandefur from Georgetown University, and he is presenting contrasting discrete and continuous density dependent population models.
Okay. Well, thank you for coming so late in the day. And this population models are something that I have just loved and investigated for a number of years. And a lot of my writing was on the discrete models. But recently, with the two journals that came out with Simiad and CODE, they got me to talking about also looking at continuous models. There's a lot that is that's in common with these models, and there's a lot of interesting differences. So I thought I would share some of these with you. First off, a continuous or a density-dependent model. The first line is a discrete one, and the second line is a continuous model, where the R is a per capita growth rate, and it's a function of the population size. So I often, if I was going to teach differential equations, I would start with the discrete version, but I would write it this way, where h is the time increment. And then you see that the per capita growth rate for the discrete model is also proportional to the time increment. But then in this form, you can divide both sides by h and then take the limit as h goes to 0 to get the continuous one. So I like students seeing the connection between these. We need to make some assumptions about the per capita growth rate. So some reasonable assumptions is assuming that there is an intrinsic per capita growth rate. So that would be B, and that would be the growth rate when the population size is near 0, because then there would be plenty of food and space available. So that would be sort of the optimal growth rate. Now, I'm not going to be talking about depensation models, which I also find fascinating, in which case the intrinsic per capita growth rate occurs at a larger population size. It does not occur at 0. So we will assume that the per capita growth rate is decreasing, so that as the population size increases, there's food and space limitations, and so the growth rate would decrease. And then we assume there's some carrying capacity. So when the population size reaches the carrying capacity, which I'll call L, the per capita growth rate would be 0. Now, for simplicity, what we can do is rescale and let one unit of the population be the carrying capacity. Now, in studying these two models, we look at the equilibrium values, and hopefully everybody can see that 0 is an equilibrium value for both equations. And also, since R of E is 0, 1 is also an equilibrium value for both equations. So what we're going to do is study these equations near equilibrium. So we linearize. So for the continuous differential equation, we take the derivative of this function with respect to p, evaluate it at the equilibrium value, and we get some value a. So near the equilibrium value, the population behaves like this function. So from this, we can see that if a is less than 0, the equilibrium value is stable, and if a is greater than 0, it's unstable. So for the population model, here's our f of p. We take the derivative, we evaluate it at 0, and it's equal to b, which positive intrinsic growth rate. So 0 is always unstable. And if you evaluate it at 1, since r is decreasing, r prime of 1 is less than 0, so 1 will be stable. Now, for the discrete model, what we do is we again take the derivative at the equilibrium value. And for the discrete model, the population behaves as similarly to E plus C a to the n. So looking at it in this case, we see that if a is less than 1 in absolute value, the equilibrium value is stable. And if a is greater than 1 in absolute value, it's unstable. So applying that to the discrete model, notice for the discrete model, when you take the derivative is 1 more than it was for the continuous model. So when we evaluate it at 0, we get 1 plus b. So again, 0 is an unstable equilibrium. And when you evaluate it at 1, you get 1 plus r prime of 1, which is less than 1. But here's a difference for the discrete model. R prime of 1 has to be greater than minus 2. Otherwise, the a value would be less than minus 1 and it would be unstable. So let's look at the logistic equation, which most of you are probably familiar with. So for the logistic equation, you just assume the per capita growth rate is a straight line. So this is what it would have to be to satisfy our 3 conditions. So here is the continuous logistic equation. Here's the discrete one. E equals 0 is unstable for both of them. The continuous problem, one big difference between it and the discrete is we can solve for p using partial fractions. You actually get something that is not very useful, but you can still find a relation for p. For the discrete model, I have seen 1 or 2 cases where they could actually, for some values of b, find a solution, but generally you can't find a solution for the discrete model. So this is another difference. Now, for the discrete model, what we have to have is that r prime of 1 has to be greater than minus 2, which means that b has to be less than 2. So if many of you have seen this example, when in the discrete model, if the intrinsic growth rate is too large, you get, it starts a 2 cycle, and then you get a 4 cycle, and you get a so forth, and you actually get period doubling to chaos. The other things, if b is greater than 3, almost all starting values have the population going to minus infinity. And if I've got this thing in my way, so I can't read the bottom of my screen. If p of 0 is greater than 1 plus 1 over b, then p of n goes to minus infinity. So the logistic model is really not a good model for population growth. Originally, May had looked at it, and he wrote about it because he felt that it had interesting mathematics behind it, but not that it was really a good population model. If you're interested in the period doubling to chaos, so here we are, it's increasing. We get the equilibrium becomes unstable, stable 2 cycle, stable 4 cycle, and so forth. And if we keep increasing the b value, you get this bifurcation diagram. I circled this area of this diagram because in here you see this stable 3 cycle. And Jim York proved many years ago that if there's a 3 cycle, you have chaos. Of course, you have to figure out what his definition of chaos is, and there's a number of those out there. Okay, so let's go back and look at more reasonable per capita growth rates. So given our 3 assumptions, well, we think the logistic equation is not a good model. you could have something that's concave down or something with a point of inflection. And these two per capita growth rates correspond usually to species that exhibit scramble competition. And by scramble competition, what we mean is this, all of the individuals in this species are equally adept at finding resources. So what happens is, because they're all equally adept, they all are, for low population sizes, they all sort of survive. And then all of a sudden, as you increase toward the carrying capacity, you get a big drop in the per capita growth rate. Now, the concave up case is often, and the scramble competition is often prey species. The contest competition, which is concave up, tends to be for predator species, and it's often species in which there is a hierarchy in the ability to gather food and space. And these might be species where the mature adults or the adult males are better adept at finding resources, or there's a movie, Monkey Kingdom, which this Monkey Kingdom, there's a hierarchy among the monkeys in this group. And so the large lower group gets the poorer resources. So here you might have, as the population increases, this larger group drops quickly, and then it starts leveling off. Now, for the discrete model, you cannot have the per capita growth rate go below -1. If it went below -1, it would say more than 100% of the population died. And that doesn't make any sense. And that's what went wrong with this logistic model. So for the discrete model, we have to have this additional assumption. Now, if we want to develop a model, well, one, we could try a rational function. And if we start applying our conditions, so we let R of 0 be B, it gives us this one, and then the R of 1 being 0, and then that it's decreasing. If you take the derivative and you want it to be negative, you find that A4 has to be positive and J2 has to be greater than or equal to J4. Now, if we want to add our discrete problem, then as R goes to -1, J2 has to equal J4, and the A4 equals B. So this is the one model if you're using a discrete rational function. And it was first studied by Beverton Holt in 1957 using J equals 1. And then Maynard Smith's, and they were studying a, prey, let's see, I think a prey species, and then Maynard Smith, Slatkin considered it with J not equal to 1. So if we want to know whether it's scramble or contest competition, you take the second derivative, that's it here. Everything's positive, but this one term. And if you look at this term, if J is great, it is between 0 and 1, it's concave up and it's contest competition. And if J is greater than 1, there's going to be a point of inflection and you get the scramble competition. So this, as we see, the scramble species with scramble competition tend to approach equilibrium very rapidly. Those that satisfy the contest competition approach the equilibrium more slowly. And then in another paper, I talk about how this affects if we were trying to do sustainable harvesting and maximizing profit, but I won't talk about that here. If you're trying to find a solution for the continuous model, we can take this equation. If the J's are integers, we can do separation of variables in partial fractions. So theoretically, we can find a solution, but I've done it in a couple of simple cases, and even in the simple cases, the solution, you get the relation, you just can't make heads or tails out of what's going on with it. So as Frank's heard one of my talks before where I made this point, that solutions are often overrated. The linearization is really in the more type of behavior we're interested in. Quickly, the exponential, if you want to model with an exponential per capita growth rate, you apply these same conditions again, and adding our fourth condition, the exponential has to be of this form, and that's the classic discrete Ricker model developed in 1950 or studied in 1954 with J equal 1, and then Bellows in 81 studied it with J not equal to 1. So we know that zero so for these models, we know that zero is unstable. For equal 1 is always stable for the continuous model. Now, I would argue that most species have at least some discrete portion to them, so discrete models might be better. For the rational model, it's interesting. If J is between 0 and 2, then 1 is always stable, and you have a nice bifurcation diagram. If J is greater than 2, then 1 is stable only if B satisfies this particular relation. For the exponential model, for any values of J, if B is too large, E equals 1 is not stable. So for B would have to be less than this particular one. So for the one where J is 1, you get that B has to be less than E squared minus 1, which I sort of find interesting. So in both these cases, you again get period doubling to chaos. So if J is greater than 2, or for the exponential model, always. And again, for the logistic model, once the intrinsic per capita growth rate reaches 3, everything collapses. But for the rational and exponential models, you get this bifurcation diagram just keeps going on and on. You don't get this collapse happening to it. My talk was based on a lot of the stuff with the discrete model. Well, let's see, I'll start off. This first, and it talks about the population growth and develops these particular models, but for differential equations. And it's sort of a part 1. And the second paper, which also came out recently, in fact, it came out before the first one, but was written several months after the first one, uses what's been developed in the first paper to develop relationship about sustainable fishing and making a profit. And one a good model is something that comes up with something that's unintuitive. And actually in this paper, you see that maximizing your profit actually results in you lowering your rate of harvest, which some people think, oh, maximizing profit might be damaging to the population, but maximizing profit is actually beneficial to the population you're harvesting. Paper, which I did all of this material in the discrete version. And then I also have, had a textbook, Discrete Mathematical Modeling Theory and Applications, was published by Oxford a number of years ago. It went out of print. I've rewritten the first part of this, self-published. It's a PDF. I personally think it would make a great one semester upper level math course. Now it is discrete and not differential equations, but anybody that's interested in it, I can send them a copy of the PDF, and they're free to use it. Okay, so thank you very much for coming at such a late hour.
It looks like we've got a question in the chat.
Oh, okay. Okay, let me go find. Where did it disappear to? All right. I'm sorry, I'm having, let me, and I may have crashed. Okay, I'm back. Sorry about I was worried about that. Okay, and then there's a comment in chat. And let me see if I can. Check. Oh. Question in chat. Let's see here. Okay, I'm not seeing.
I could read it out for you if that's a little
Okay,
bit.
thank you.
Okay,
Yeah.
I was going to. Sorry.
So the first question says, how can we control with too much deer population?
How can we what, Neil?
Control with too much deer population.
Well, I mean, this is something I can only make guesses at. I mean, we did have deer with predators in, and these models are they're not predator prey models. So really, if you're looking at trying to study keeping control of deer, you would want to use a predator prey model. Other models will look at age structure, and what's happening is you get too many deer, and I would guess that they're very similar to the scramble competition. So what's happened is the population will increase, and then they eat up all their resources, and you're going to get that where all of a sudden, if we didn't control them, you would get this big crash. But then they expand out into other territories too. So this is one limited territory. Okay, is there another question?
Well, I just had a comment, if you don't mind,
Okay.
James. The, I know the deer population are being hunted here, and and a lot of population are being hunted. But a friend of mine talks about the wild hog population, how bad it is in Arkansas, where I grew up. He has to go out and kill a large number of hogs, and I'm wondering if any of this is applied toward that type of population.
Well, okay. What I did here is sort of describe what's happening, what can happen with populations. And in these couple of papers that I've written, I introduced the harvesting or hunting and how that would affect it. So when you're talking about like going out and killing the large number of hogs, that would really be in that hunting paper. And what you do is if you hunt at a certain rate, and what it's usually called is the constant effort model. So if you take the same amount of time hunting, you're going to kill the same proportion of the population each time period. So instead of going out and hunting a particular number of hogs, you hunt for a particular amount of time, and that will get it so you have a proportional harvest. And if you do that, you will reach an equilibrium. And so you sort of have to decide what equilibrium you're comfortable with, depending on which you can control by that the time you spent hunting or the number of people that are hunting. So unsatisfactory answer, but if you look at the harvesting and hunting models, it helps you understand. Yeah, in these papers, I try to develop things that help you understand public policy. What would be good policies to help in different situations? And that the hunting license for the deer season, hunting for the hogs, that would be in that realm.
Yeah, I thought it was a good explanation. I appreciate it, and I know that every year they adjust the limits and things on these so to balance things out.
That's right, because you're going to have other things in the dry season, wet season. So there's going to be other things that would. So some seasons they do this in the fishing industry also. So some years there's going to be a bigger population, and you can let them hunt or fish for a little longer. Other years, other things with the environment or the ocean or whatever happen and drive the populations down. So you've got to shorten it. Okay. Are there any other questions?
Yeah, James, I was just wondering the second edition of your discrete dynamical systems book that you mentioned, PDF, is it also going to be available for purchase as a paperback?
No, but it's an interactive PDF, so you can clickable. Yeah, I'm willing to supply it to you. If you wanted to print it out for your students, that would be fine. But you can also just look at it and give it to your students as a PDF.
I see. Thank you.
I personally find now that I've been doing a lot of these PDFs, I find reading the PDF better than reading the book. I can just move around a lot easier.
So true. Yes.
But just if you send me an email, then I can send you a copy of it.
Oh, great. Thank you very much.
And anybody that wants, if you look at it, I would appreciate anybody's feedback too.
Hey, Jim, great talk.
Thank you.
I have a question. So when you contrast discrete and continuous population models, some of the weird behavior, or maybe unexpected, at least at first, behavior of discrete models is really due to the fact there's a time delay, not that it's discrete. And you can model that with continuous models with time delay built in. I just wondered if you'd care to comment on that at all.
Well, the discrete systems, I'm not sure it's all time delay, because you've got a lot of species that have breeding seasons, so that you get this big jump at one particular point in time. So the discrete and
Sure, but for example, you can get 2 cycles with a continuous model and time delay and a fixed time.
okay, yeah. Can you get it? And you get the time delay? Can it result in four cycle or even chaos?
I don't know. I mean, I suspect that if you had, I wouldn't be surprised if it could.
Yeah.
Basically, it's a question of dimensionality as well as I mean, if you're talking about time delay of 1 unit at a time, you're really talking about 2 variables. One that's lagging behind. So
right.
We always talk about the difference between the discrete and continuous. We talk, for example, about temperate zone insects or anything else that's linked to that. But in fact, there are other factors that might be involved.
Yeah. Well, I know because there's an economic model, the discrete economic model I've looked at, and you can put in this control. And if you put in the immediate control, you can take an unstable system and make it stable. But if there's a delay in your control by government inaction, then it can destabilize a stable economy. So I'm familiar with the thing of delays can often backfire on you.
Right. Super. Thank you.
Okay. Well, thank you. Thank you.
Thank you.
Appreciate it.